let's talk about units for a couple minutes here. So a unit is a known quantity of something. It's something that we can all agree on. For example, a meter. A meter, we all can agree on how long that is. And this is important for science because if we want to compare results or ideas, either between your experiment and my experiment, or between my experiment and one that was done 100 years ago, or between my experiment and one that's done 1,000 years in the future, we need to know what we're referring to when we're talking about things. And so that leads us to, we have two major unit systems that are used kind of globally. First, we have SI, or the metric system, and this is the one that we actually care about for this class. This is standard for math and science. It's the far and away most common unit system that's used globally. But there's also the English or imperial unit, and that's used in the US, Liberia, Myanmar, and occasionally for a couple things in certain other places. But most of what we're going to do here is metric, which I think most of you are already familiar with, and so let's talk a bit about that. When we look at units and unit systems, we want to talk about fundamental units first. They're the most basic ways to measure the universe. So these are the 7 basic ways we can measure the universe, the 7 quantities we can measure about the universe. We've got length, which is measured with meters, mass, which is measured in kilograms, time, which is measured in seconds, electric current, which is measured in amperes, temperature measured in Kelvin, amount measured in moles, and then luminous intensity measured with candela. So all of these fundamental units are defined by universal constants, or at least what we believe are universal constants. So this means that if we take our definition, as long as we write down, here's how we define a meter, here's how we define a kilogram, etc., and we include that with all of our documentation, we can send that, millions of years in the future, we can send that to some alien civilization, and as long as they can understand how we defined those units, they should be able to compare their work to ours. And this is important because we want to be able to do that. Interestingly enough, as an aside, the mass, or the kilogram, was just recently, as of a few years ago, defined by fundamental constants. Before that, say 5 years ago, the kilogram was defined as however much mass the kilogram in France, which was just this basically block of metal in France. So however much mass that block of metal had, that was the definition of a kilogram, which is problematic because if you went in and shaved a bit of it off, the kilogram would suddenly be less than it was before. And that means we have a whole mess because it would look like all of our rules change and constants change and blah, blah, blah. So that's why we, as a scientific community, work to redefine that based on some fundamental constants and values. But you might be thinking there's a bunch of other units that you've heard of, and those would all be derived units. And those come from combining the fundamental units. So here's some examples. You've got velocity, which is meters per second, density, kilograms per meter cubed, atomic mass, kilograms per mole, force is a kilogram per meter per second squared. So you can see how all of these are combinations of some of those units on that previous page. So when you combine them, you can get additional units.